So it's a great pleasure and honor to be here today representing Optalysys. Got my clicker? So I'm guessing most of you have never heard of Optalysys. We're pretty new to the Web3 scene, and I'm fairly confident that some of the stuff we show you today you won't have seen before. So hopefully it'll be interesting. You won't be thinking about sandwiches. My job is to keep you interested for 20 minutes. So my name is Nick Lawrence. I'm VP Product at Optalysys. So let me introduce. I'm going to be talking about the route to mainstream adoption. So from our point of view, what are the big things that we think are needed for this to go mainstream? Let me start by introducing the company. So we're a pretty unique company in terms of our skill sets and the diversity of what we do. So we're a UK company. We're venture-backed. We've got two main offices in the UK, in Leeds and Bristol. You can see a lot of the team there. At heart, we are a photonics company. So we develop chips, not just silicon processing chips, but using lasers and optics to make it go even faster, even lower power. And 2 or 3 years ago, Web3 blockchain became a new market for us. So it's one of the 3 markets that we work in. So as well as Web3, we also work in secure database and in secure AI machine learning. So we're trying to develop the future of secure computing, and on the next slide we'll show where we fit into the stack, because this industry is all about working together in different capacities. So this is our view of the stack. So at the top you've got the developers building the cool dApps. Slightly lower down you've got the people building the platforms, so people like Fhenix, Zama, Inco. Underneath that, you have the low-level FHE libraries, the encryption libraries. So TFHE, RS from Zama, and the open FHE libraries for the vector schemes. And then under that, you have the hardware layer and the API layer to the hardware. And that's where we sit. So our goal is to make the best infrastructure layer that's going to be used by everyone. We're a very partner-oriented company. We want to work with everyone. We want to be super easy to work with. So hopefully that lets you understand where we sit in the ecosystem. So what are the 5 things that we think are needed in order to make FHE go mainstream? You know that you've gone mainstream when your name is in lights in Las Vegas. So I'm going to propose 5 things. Firstly, there needs to be a reason to do it at all. What is the economic incentive to use FHE? The good news is, I think it's a no-brainer. So if you're a business, if you're trading with partners, customers, supply chain, would you really want to publish every financial transaction, put it on a billboard, hand it out? Of course you wouldn't. It's commercially sensitive. So blockchain by design is transparent. There is a real basic business use case for adding confidentiality to blockchain. So obvious economic reason. And then getting into specifics, MEV protection, protecting a plain text mempool is a good example. And I like this quote by Jeremy Allaire. So he is the CEO of Circle. They launched the USDC stablecoin. They've just gone public in the US. And he says the biggest barrier to widespread enterprise adoption of blockchains is privacy. So we're using that quote a lot because we agree with it, and he's a pretty well-known guy. Okay, so tick in the box, we have the economic incentive. Secondly, this will all fall down if there isn't the right regulatory framework in place. And luckily, we're now in a much better place than we were a few years ago. So 2 sort of buckets of regulation. So on the one hand, you have things to do with personal data and privacy protection, GDPR, CCPA, DORA, which drive demand for a privacy confidentiality solution. And on the other side of the room, you have the legislation that gives clarity to those people building systems. So MICA in the UK, in the EU, and obviously the Genius Act, which has just been going through Congress in the US. It gives everyone in the industry confidence that they can build and know where they stand from a regulatory point of view. So that is also falling into place. So 2 for 2, I reckon. Thirdly, we need a mature software platform. And I think I'm glad that I didn't go first, because you've already seen earlier in the day there's some really cool stuff being built. The coffee platform that Fhenix had, first talk, it's a good example. Zama are doing great work, trailblazing in this space. It's really starting to mature. There's still more work to do, but we're definitely getting there with that. Fourthly, and hopefully some of you here will be directly making a difference here, we need the developers, we need the ecosystem, we need people building the dApps, people optimizing the user experience, people thinking about the ordinary person in the streets and how's this going to make a difference for them. So that's a really important part of the system. And I think we have some of that, and there is more that we can do. And then finally, and this is the bit which is kind of relevant to us and that I'm going to talk about for the rest of my talk, is the scalable infrastructure. And what do I mean by scalable? So obviously scalable means it will grow with demand. And why is it important? So firstly, I suggest that throughput drives opportunity. And let me give you an example. So what I've tried to do here is I've listed some top blockchains. And for each one, you've got two figures. You have the max historical transactions per second. So what's the fastest they've ever been recorded at running at? And what's their theoretical maximum according to the maths and the way they're set up. And you can see there's some pretty big numbers. So obviously Ethereum is pretty much the slowest. But there's lots of L2s, lots of faster blockchains that are in the hundreds, thousands, getting up to tens of thousands. And so if we're really going to claim that confidentiality and privacy should be an integral part of all transactions, then we need the infrastructure that's going to support that kind of level. So that's part of what drives our vision. That's why we're really focused on building faster and faster hardware. And I'll explain in a minute what we have today and also what we're going to have in the future. And just at the bottom, for a little bit of motivation, I've included 3 well-known non-blockchain payment platforms. Look at those transaction rates: 40,000, 65,000, 325,000. We want to be able to get to those kind of rates eventually. So you're going to need some serious hardware to support that. I would suggest laser-based photonic hardware, maybe. And but it's doable, and hopefully I will persuade you why that is the case. Obviously, related to that, it's not just a case of can you put more and more servers together. It's how much is that going to cost you? How is it going to cost you to run? How much power does it consume? What's the sort of upkeep and maintenance part of that? And we have taken a slightly different view to everyone else making hardware at the moment for FHE. So my slightly generalizing explanation would be most people will say, here's a bag of bits, go and put them together, and you've got to run it and manage it. And what we're trying to do is to give more of a total solution. So we're trying to aim for an enterprise-grade solution for FHE acceleration. And I actually have some more interesting interactive pictures to show you. So let me show you. Let's see if this works. Do I click it one more time to make it run? I don't think the video works. Or maybe it does. It's teasing me. Thank you. So this is what our product looks like. It is a server blade, a 2U high server blade that fits in a server rack. Inside the box, we have 3 FPGAs from AMD, V80s, and we have a pretty chunky multi-core CPU. And it's actually the combination of the CPU and the FPGAs that allows us to hit our performance. So here's a non-moving summary. So as I said, that's what's in the box. It's a 2U rack. The headline performance level we're defining in terms of transactions per second. What is a transaction? It is a confidential ERC20 token transfer. So that is Alice sending Bob some tokens, but in a confidential way that hides the amount that's being transacted. And compared to other hardware solutions like GPU or CPU or other FPGA solutions, we believe that we have best performance, price, power combination. And by making it available in this form factor and also working with partners, we believe it's suitable for deployment in private data centers, in public cloud, and in colo. And we're happy to talk to you about exactly how we would do that. We've got a stand outside afterwards. Third aspect of scalability is, so imagine that you think, okay, that's cool, I'm going to invest in some of that. How do we help to make you confident that your investment is going to be worth it in the medium term, that you're not going to need to spend lots more money in the future? So let me tell you a little bit about our roadmap. So our current product, our Gen 1 product that we announced a couple of weeks ago, is based on CPUs and FPGA, so programmable silicon. We are already well into developing our Gen 2, which is a digital ASIC, and we're going to have some of those next year. And then the super fancy version, the ones with lasers and silicon photonics, are going to go like the proverbial clappers. They're a year or two after that in our roadmap. And by designing our system as we have, there's kind of a smooth upgrade path. So you can take out one card, you can replace it with a next gen card, and it will keep working. So that's the plan. Okay, so I'm claiming that we have best in class performance. How do we achieve that? So I've got 4 slides to try and walk you through it. So a lot of you will know this. So business logic is actually defined in code via smart contracts, so written in Solidity. It might describe things like transferring tokens from one person to another. Each transaction, as we've seen a slide or two before, you have low-level FHE operations. So you might have an add or a subtract. And the way I like to think of it I like to always simplify things in my own head. Each operation has a different shape. And by shape, what I mean is how long it takes in linear time, and also to what degree it can be parallelized and run in parallel. So it's like a Tetris block. And the sort of simple way of thinking about it is, okay, my transaction has 4 operations. I've got to put my 4 Tetris blocks in a line. What's my latency? My single transaction latency is just the x direction. It's the length of those 4 blocks. That's fair enough. So if I start to put it through a hardware platform like a GPU or an FPGA, think of it like a data pipe. So you're trying to fill that pipe as full as you can. You're going to try and stuff as many through as quickly as you can. And it's a little bit like putting lots and lots of Tetris blocks through it. Now the challenge, as you can see, is there's a lot of grey space. So it's not necessarily the best way to fill the pipe. You kind of waste capacity. So what we do is more like playing Tetris in real time. So because we're not trying to do everything on the FPGA, we use the CPU to do the scheduling, and we just accelerate certain parts on the FPGA. And the net result is we can pack that pipe out, minimize the wasted space, and maximize throughput. Okay, let's see if this works. So what we have now is a demo of a DApp sending tokens from one person to another, I think from Bob to Alice, and there are 4 low-level FHE operations that it's doing. So when I said it has an add and a subtract, it's because you have to check the balance. Do I have enough in my account in order to send the tokens to the other person? And then you subtract from the sender and you add to the receiver the number of tokens. So let me show you in practice what that looks like. Okay, so on the right is Bob, on the left is Alice. So they have encrypted balances halfway through, which is that long list of numbers. They can ask to decrypt that balance and see it in the plain text. So you can see they each have a balance of 50 halfway up. So Bob wants to send 10 tokens to Alice. So he chooses 10. He has to encrypt that value. And when he does that, he receives back a handle, so a pointer to the address where the ciphertext is stored. And there's also a zero-knowledge proof that proves that he's encrypted it correctly. He then puts in the address he wants to send it to, which is Alice. And then I think I have to click this one more time. So he then wants to transfer it to the receiver. He has to confirm. And if you were eagle-eyed, you might see that the encrypted balance at the top has changed from one squiggle to another squiggle. So Alice then can decrypt her balance again, see what the new number is. So she decrypts it, and her number has changed from 50 to 60. And if Bob goes back and decrypts his balance, his will have changed from 50, hopefully, to 40. There you go. So we have a completely encrypted balance transfer, token transfer between two parties. Okay, so next thing I want to show you is a sort of performance comparison. So we're a hardware infrastructure company. So we're going to show you 2 NVIDIA GPUs running. So the purpose for this is, it's all very well to say single transaction latency is a key metric, but actually in a real system, when you've got hundreds and thousands of transactions going through it, we argue that the more meaningful metric is what is my latency, what's my experience as a user when I use this system. So so what we're doing is we're sending 1,000 transactions through the system, and we're plotting it for GPUs and our system. And so you're going to see, I'm going to pause it halfway through, and you're going to see how it starts off and how it proceeds. So the green chunks are the GPU, so they process them in blocks of about 20. And you can see that the first block of 20 happens in 0.4 of a second, and it's slightly faster than the first 20 going through our system. But after that first block of 20, ours overtakes the GPU and gets faster and faster and faster. And so as you run the whole transaction, we get through 1,000 transactions in under 10 seconds. So that's our 100 transactions a second metric. And the GPU takes almost twice as long. In fact, it's not even finished on this graph. So just showing you visually why thinking about bulk transactions is actually, in our view, a better way of thinking about it. And that has led us to our architectural decisions. Finally, this is something a little bit different, but given that some of the audience are going to be developers and maybe people writing smart contracts, we've written a little tool. So what this does is it allows you to choose a smart contract. So we have 3 example smart contracts as the top 3 icons. And then the 4th icon is you can upload your own smart contract, anything you like. And the tool analyzes the smart contract. So in this case, let's choose the basic confidential ERC20 smart contract. So within that, there are encrypted variables and there are FHE operation calls. So the tool can analyze that. So first thing it does, once you've selected which contract you want, it will parse it and say, okay, I found a bunch of function calls in here. Which function call do you want to run for your use case? And how many transactions a second do you want to support? So maybe you are running a blind auction and you want to support 1,000 bids a second or something like that. Or in this case, it's a ERC20 token transfer, and you say, I want to support 150 transactions per second. So, okay, that's what I'm aiming for. What hardware will I need? So before we tell you which hardware you need, firstly, you need to tell us what kind of network architecture you want. So these are FHE coprocessors, and you have a choice of running them in optimistic mode, where you have a single coprocessor node, or in consensus mode, where you have multiple coprocessors working together and they vote on what's the right answer. So I think, for example, in the Zama testnet, they have 3 coprocessors working in consensus as their default. So I think we've picked 3 in this case. So that's my last input step. It will then summarize what you've asked for on the left, and on the right it will say, okay, for this hardware model, how many Lightlocker node servers do you need for each coprocessor node? So in this case it's 2. 2 will give you 200 transactions a second for this type of operation. If you need 3 consensus nodes, then in total you'll need 6 hardware boxes. Now this is the kind of obvious example because the token transfer metric is the one that we've been using as our 100 transactions a second metric, but it's a lot less obvious when you get into other operations like a mint or a transfer or a blind auction bid. This tool gets really quite useful for you to look at what you're specifically interested in, what performance levels you want, how does that map onto hardware. So I'm pretty much out of time. This is what I've talked about. These are the 5 things that we think are necessary. All that remains to say is, between us, I think we have all the bits that we need. Let's make it happen. We're excited to be part of this community, and we're all about partnerships. And as you're getting your sandwiches or your food, we are there in the corner. We have a table. We have a Lightlocker node piece of hardware, I think, to look at, and we would love to come talk to you. Okay, thank you very much.